Hello everybody, welcome to my work for the second lab in this course. The question is, what happens when net force isn't zero? According to Newton's second law, the velocity change. How? Oh, it can change magnitude, direction, or both of them. A paperball falling from the rest is a good example for this. When the net force is not zero, velocity isn't constant. We can see the paperball falling from the rest. To study this motion, we need a scale, 60 centimeters, axis, one of these vertical, and so we can obtain these results about position in meters and time in seconds. We will put these figures on a spreadsheet. We want to compare these results, this observed result, with result from theoretical model. We use two models. The first one, there is only one force, the weight. So net force equals the weight. The weight is always pointing at floor. Weight equals mass times g. G is the gravity acceleration. And the second model, we consider two forces. The weight, represented by blue arrow, and drag. Drag is dependent on the velocity, isn't constant, and is always opposite to the weight. It's represented by a green arrow. We use a program to obtain the theoretical results, and inside we need to assign the initial condition like mass, ball position, ball velocity, and time. This is the expression for weight. It includes mass, gravity acceleration, and a unit vector j hat. In this fragment of the codex, we make the calculate for net force equals weight, only weight. We obtain the ball velocity and the ball position, and in the another fragment of the codex corresponding to the second model, the net force equals weight plus drag, and the drag is equals ball velocity times ball velocity times b. B is a factor equals 0.00228 times g hat. We obtain three sets of results, position versus time, corresponding to predicted position with a drag, observed position, and predicted position with drag. In this graph, position versus time, we observe the good agreement between predicted position with drag and observed position. When the velocity increased, the drag became higher and higher. But it's not a good agreement between observed position and predicted position with two models at the beginning of the motion. We can see a constant velocity with drag model with time. Perhaps it's not enough time. What was wrong? Oh, perhaps there might be an initial velocity, so the observed position is below the predicted position, and there was a light breeze who pushed the paper ball. That's all. Thank you.